The last test that we're going to learn in this class is the chi-square test of independence. So first of all, just a reminder that capital X is the Greek letter chi, and sometimes we write it CHI. It is not pronounced chai. That is a synonym in the delicious tea. So we've used the chi-square test before when we're doing the chi-square test of goodness of fit. And it is a way of measuring how far away a count of a particular category is, that the count that we've observed is from the count we've expected. So you take the count that's observed, you subtract the count that's expected, you square it, and then you divide it by the expected. And that's going to give us roughly a number. So if our observed is being drawn from a population where what we expect really is going to happen, then this value is going to be roughly distributed the way a squared value would be drawn from a standard normal distribution. So the big difference in the chi-square test of independence is how we come up with the expected values. So to review goodness of fit, we got our expected values in a chi-square test of goodness of fit from a pre-existing hypothesis. So either we thought that every category was equally likely, which is the simplest hypothesis, or we used some aspect of the real world to generate probabilities for each group that we expect to see. And so there's an expected proportion. We multiply that by our sample size for each group, and that gives us the expected count. For the chi-square test of independence, we use the marginal totals for each category and compute the expected totals for each combination of category. Because we are working with, when we're doing a chi-square test of independence, we're working with two discrete variables, two different ways of dividing our observed items into groups. So for example, if we're talking about something in baseball, one way of dividing baseball, and players are a unit of observation, one way of dividing players is into left-handed or right-handed players. Another way of dividing them is into people who are catchers and everybody else. So those are two discrete variables. And for each person, our observation would be left or right-handed and catcher or non-catcher. And so if we think that there's no relationship between what hand you throw with and what position you play, then what we'd expect is whatever proportion of catchers that we see in the population times whatever proportion of left-handers we see in the population should equal the expected proportion of catchers. And so the math for that works. You don't actually have to compute the proportions. If you look at 40 people, and then 4 of them are lefties, and 3 of them are catchers, then you multiply that 4 by 3 to get our expected, and then divide by 40, and that is our expected count. So we expect to see about 3/10 of a person would be a catcher. So if we had a much bigger team, we might expect, or a much larger sample, we might expect to see that eventually get up to see 1 catcher. So, in other words, the number of people in one group times the number of people in another group divided by the total of your sample, and that's your expected count for your cell. And then you look at how many people actually occur in that cell, or items, and then that is going to be your observed, and so then you can do a chi-square test as normal. So, since we're looking at two different groups, we have to compute degrees of freedom slightly differently than when we were computing it for chi-square test of goodness of fit. Basically, if you remember the chi-square test of goodness of fit, you have the number of groups minus 1. And so we take the chi-square goodness of fit type degrees of freedom for the first variable, and we multiply that by the chi-square test of goodness of fit type degrees of freedom for the second variable, and that gives us the total number of degrees of freedom for our chi-square test of independence. So if there's 10 groups, 10 positions and 3 kinds of handedness, that would give us 18 degrees of freedom. But in my simple example, there's 2 different kinds of group, 2 different positions, catcher or not catcher, and 2 different handedness, left or right. And so that would give us 1 degree of freedom total. So the null hypothesis in a chi-square test of independence is that there is no relationship between our two discrete variables, so that knowing something about whether you're left-handed or right-handed doesn't give you any information about whether that person is a catcher or not. And similarly, knowing something about whether someone is a catcher doesn't give you any information about whether they're left or right-handed. So that is like a correlation, but it's with discrete variables instead of continuous variables. So it's a measure. So that, again, the null hypothesis in a correlation is that there's no correlation. How far something in the x variable is from its mean doesn't tell you anything about how far a variable is from the y part of its mean. So it's another one of these double negative things, right? We're trying to, if two things are associated, that means they're not independent. So if we can rule out that they're independent, the remaining interpretation is that they're associated. So the p-value gives us the probability that we would observe the data that we have collected if the two variables were actually totally independent of each other. So a small p-value means that it's less likely to see it if they're independent. So it means that we are more likely to think that they are associated. So we found some support for association. So I'll go through an example here using some data from students. So there are two kinds of operating systems in Carthage generally, Mac OS and Windows, and there are two kinds of smartphones generally, iPhone and Android. And I know it's super classist to assume everyone has a smartphone, but we'll move on that. So a typical collection of Carthage students, oh, this is a little small because I collected this from people who graciously showed up for class, shows that there are so there's 10 people with iPhones and 4 people with Androids. So that's the margin for phones. There's 7 people each for Windows and Mac. We can see that there's 3 people who have an iPhone and a Windows machine, 7 people who have a Mac and a Windows machine. I'm sorry, a Mac and an iPhone. 4 people who have Android and Windows. That includes me. And 0 people who have a Macintosh computer and an Android. So these are our cell counts. So we take these marginal totals, we can compute our observed counts. We can compute our expected counts. So here, because we have 50-50 Mac and Windows, we expect to see 5 each for Mac and Windows among our iPhones people, and 2 each among our Android users. So see how the marginals are the same, the grand total is the same, but it's different in the actual counts within the cells. So if we compute the differences here, this would be a fairly large difference. They're all about 2 away from what we'd expect. And so we have, 2 squared over 2, so that's 2. 2 squared over 4, so that's 1/2. 2 squared over 5, so that's 0.8. And 2 squared over 5, another 0.8, so we have 1.6 plus 1/2 is 2.5. 1.6 plus 1/2 is 2.1, plus another 2 is 3.1. So we would have a total chi-squared of about 3.1 with 1 degree of freedom. And that would turn out to be actually marginally significant. Pretty close to significant there. This is evidence that Macs and PCs are not independent. What computer you use is not independent from what smartphone you use. And subjectively, we look at this and say, okay, well, that's going to be driven by this sucker here. Nobody uses a Mac and an Android. That's like, it's kind of defeats the purpose, right? So that's how we do a chi-square test of independence. And there's a bigger sample size, and so you would report it by saying there's a significant association between students' operating system choice and the type of phone that they use. We have this chi-squared, that's this description of the statistical test we're using. Subscript of 1, because that's our degrees of freedom. So again, the test statistic symbol, the parameters in subscripts, then equals, we give our test statistic total, and this one at 7.62 because this is a bigger sample size, and the p is 0.006. So significant association, chi-square test, one variable and the other variable. And that's how you report a chi-square test of goodness fit. And that is it for this lecture.